Going on to lesson 6.4, logarithmic properties and models. We'll start. Here are the objectives. And I hadn't pointed this out before, but up over here in the corner is a general introduction orally through the various lessons. So another backup way, other than following what I've done here. Take a moment, pause, read them through, and we'll get started. Again, I'm not going to read this aloud, but you should pause and read it through. In example 1, take a moment, pause it, read what's there. Okay, we are familiar with the continuous interest formula. But notice now we don't have the rate. So rate is an exponent. Now we know the future amount A, which is this. We know the initial investment is this. E is there. And our time is just 1. So what we need to find is the rate. So how do we do that? Well, here we go to logs because we want to find an exponent. So the first thing we do is divide both sides by 10,000. And we get this. And we have that e to the r power equals this. So now we're going to convert this side to its natural log. And keep in mind the natural log, base e of e, this configuration is just 1. So we get what our r value is then on this side. That's what they've done here. So when we take the natural log of this, we find our rate is approximately 2%. Now notice this is given as a decimal fraction. All right. Now you should try this in your calculator to be sure you know the protocol of doing it. So this is your model if you get one like this. The tricky part was over here converting this side just to r. That's why we used natural logs. In example 2 now, we want to solve 2 to the x power equals 9. Now, we saw this before. We know if this was 2 to the x power equals 8, we knew that this was equivalent to 2 to the third equals 8. So our value for x is going to be larger than 3. And if we convert this to its log form, log base 2 of 9 equals x, we still can't go any further than this. So what this does is introduce us to more background on logs, which we're going to get to right now. Now, in your notes, I would put this as background. You're going to read this over carefully, and then properties of logarithms. And there's 1, 2, 3 that we're featuring. And notice what's happening here. Say log base A of xy, and this is the answer, and this would be its condensed form. Its expanded form would be log base a of x plus log base a of y, and this is often referred to as the log of a product of the sum of logs. Now, in a few moments, we're going to show you the proof of this, but these are notes that I would put in my notes, your notes. Item 2, log base a of x over y. Here we're going to do division in a sense, is illustrated by log base a of x minus log base a of y. This is the log of a quotient, is the difference of the logs. Now I'm going to erase this because I wanted to stress it there. And then for number 3, in a sense, a background rule, log base a of x to the r power. Here the exponent of our answer goes to the front, goes from its exponent position here to in front of the log. This is sometimes called raised to the power, or the power rules. And in the power rule, the exponent of your answer goes in front. And we're going to see the proof of this here, as I say, very shortly. Let's raise it up. So in your text under Learn, there is the proof. Now, just to review what we've done, let's go back to Rule 1, which was this. And we said we would expand it by adding our logs here. Well, notice in the product rule, a to the first power, a to the, or y to the first power, is like a to the m, a to the n. We just add our exponents. So if we see that they were multiplied, the parallel way in logs would be to add the exponents. And that's what we see here for Rule 1. So we're multiplying, we're going to add exponents. Now there is a caution. Let's look, and hopefully you can see what's going on. Here we have a plus. That's not the rule. The rule is when we're multiplying, we would add. So here it's the product of these. We show addition. And this, again, we're not multiplying it this way. This is the correct way of doing this. And for division, this is not quite the same. This is the proper way of doing it. Okay, you'll have some practice in this, of course. And I did the practice already, and it was challenging. Now, the authors do have a video that go over each of these as well. That may be useful. Remember, if it's an area that's a great challenge, through repetition and study. So what we'll do, rather than my writing all of this out, we'll follow each of the solutions, and I'll give a narration as we go through them. Looking at the first one, A. Here's our initial condensed form. So what are we going to do? Well, notice it's 64 times x to the third times the square root of y. So this is in the form that we could expand. So our base is log 4. Our base is 4, 64. So we're doing this first part up to 64. Then we're going to go plus log base 4 of x to the third, just putting it apart in pieces. Then we're doing log base 4 of the square root of y. All right, now, again, we're looking to simplify and expand. So do you see that 64 is 4 to the third power? And that's where they get this. So we've done this step in partial simplification. Now we're doing this step, and you might say, what's going to happen to that 3 up here? That's an exponent of this x. Well, they're going to take it eventually, this 3, and put it out in front here. You'll see that actually they've done it here. And what are they going to do here? Well, this exponent, 1/2, they're going to take it and put it out in front, and that's what you have. Now, the tricky part here is this. Let's just make it big. Log base 4 of 4 to the third power. Now, we had said in this configuration, this is going to be useful for the practice and later the certify in your tests. What did we say this is? This is just 1. And that exponent came out in front here as a 3. So this is 3 times 1. And that's where they get the 3 from. And this is what they would look for in the answer. So pause for a moment, study it, see if you can follow it step by step. Now in example 2, this is our original. So first step is to convert the radical form to its exponential form. So our radicand becomes parentheses, and keep in mind there's a 1 out there. So our fractional exponent would be 1 over 3, and that's where this comes from. Now we're going to take our exponent and put it out in front of the log, which is this step. And if you're copying this in your notes, which I strongly urge you to do, you want to be sure you understand how each step leads to the next. Now, this is pretty much set here for this whole thing. And I would use, rather than parentheses here, I'd use a bracket. That would be better, I think. So it's 1/3 of everything now that's in here, log a of x, and this is x times y squared, so we're separating these two. And then to indicate division, it becomes negative log a z to the 4th power. Now, what are we going to do with these exponents here? Well, this exponent goes out in front as a 2, and this exponent goes out in front, and it's between the negative, goes out in front of the log, not the negative, so 4. And then this is the expansion of this condensed form here, step by step. Again, pause, go through, study. Now in example C, this is our condensed form. We're asked to expand it. So this is in scientific notation, and notice this is a negative exponent. Now, treating it step by step, it would be log, and keep in mind this is the common log base 10, so we don't write the base, log base 10 of 2.7 plus, since this is this times this, log base 10 of 10 to the fourth. And notice something special is going to happen here, because this is base 10, base 10. This is going to become a 1. We're going to take that 4, put it out, and there's our 4. Oh. Now, since this is division, we're going to go negative log base 10 x to the negative 2. All right, as you probably can see, we're going to take this negative 2 exponent, put it in front of the log. But notice now we have negative of a negative 2. Can you see that makes it a positive log? Okay, now where did this 4 come from? Let me write it big for you. Log base 10 of 10 to the fourth. Our exponent goes out in front, and this configuration, log base 10 of 10, is just a 1. So this simplifies to the 4. And you saw how we got a positive 2 there. Now, what is this? Well, we can take the log of this, add 4 to it, and we get this, and we're left then just with 2 log of x. Again, this is 10, and that's as far as we can go. Now, it's not yours until you do your practice and get these answers correct, but this is using the new background items of logarithms to go from a condensed form to an expanded form. Now, you probably are going to think, do we ever go from an expanded form to a condensed form? Yes, that's coming up. Now, here in example 4, they're going from expanded to condensing logarithmic expressions. And to give you a little change of pace, we'll let the author help with the instruction. We're going to take a look and include this video here. Now keep in mind you can play it at a slower speed. I tend to talk slowly. You could play mine at a faster speed, but let's let you make that decision.
In the following examples, we will write sums, differences, or multiples of logarithms as a single logarithmic expression. Our example says use the properties of logarithms to condense the following expressions as much as possible. That is, rewrite the expressions as a sum or difference of as few logarithms as possible. Example A, I have log base 3 of x divided by 3 minus log base 3 of 1 divided by y. Note that both of these logarithms are base 3. If they weren't, it would not be possible. But they are both base 3. Let's begin by taking care of this coefficient 2 and drag it over to be an exponent. So I have log base 3 of x divided by 3 squared. And I'm actually going to do the same thing with my negative sign. And I'll make this plus log base 3 of 1 divided by y to the negative 1. This will equal log base 3 of x squared over 9 plus log base 3 of y. And now because this is a sum, we'll want to condense these two logarithms into a single logarithm by multiplying arguments. So I have log base 3 of x squared times y divided by 9. We have condensed our two logarithms into a single logarithm, and it equals log base 3 of x squared y divided by 9. Example B, I have the natural log of x squared minus 1/2 the natural log of y plus the natural log of 2. All of these are natural logs. We do need to have the common base here. The base is e. Let's begin by taking care of the coefficient 1/2. So this will be the natural log of x squared minus the natural log of y to the 1/2 power plus the natural log of 2. And now these two logarithms are being subtracted, which means our arguments will be divided. This is the natural log of x squared divided by y to the 1/2 and plus the natural log of 2. These two logarithms are being added, so we'll combine their arguments with multiplication. I get the natural log of 2x squared divided by y to the 1/2. This is a good simplified answer. Or if you want, we can have the natural log of 2x squared, and instead of y to the 1/2, we can say divided by the square root of y. Both answers are fine. So we've condensed our three terms in the original logarithm down to one single logarithm, the natural log of 2x squared divided by y to the 1/2. Example C, log base b of 5 plus 2 times log base b of x to the negative 1. So we're going to condense our two logarithms. First, I'll take care of this coefficient. This is log base b of 5 plus log base b of x to the negative 2. And now because these two logarithms are being added, we will condense to a single logarithm and multiply the arguments. So this would be log base b of 5x to the negative 2. That's a good answer, or if you want, you can write log base b of 5 divided by x squared. Since an x to the negative 2, we can move the denominator. So our sum of two logarithms has been condensed to the single logarithm, log base b of 5 divided by x squared.
And I want to remind you that you can go back to the Learn yourself as you do this to view and at your own pace and read carefully what's going on. An important note here is that often there will be multiple orders in which we can apply the properties to find the following or the final results that are shown here. We'll pause a little bit if you'd like to see it. And I like the idea of the explanation to the right. There's B, and there's C. Again, pause as needed. As we continue for background information, we're going to take a look at what is called the change of base formula. Well, we still have our old friend log base 2 of 9. What method can we use now to actually solve this one? Well, they're going through it in steps. Let me just review this, and I'll do a right over here. So we could put this in log form. We're going to say this is going to equal x. X is the exponent. So that's what they've done here. So this was in its exponential form, base 2 of x equals 9. Now we can change this by using logarithms. We'll take the log of this side, the log of this side. And we're going to use natural logs here. So that's what they have. So we're going to take our x, put that out in front from what we've just learned, and we now get x, natural log of 2, equals natural log of 9. Now, if we want to use our algebra skills, how do we isolate x? Well, we divide both sides by the natural log of 2. Natural log of 2. And that's what they're doing. Now, when we simplify this, and I'll have to move it up, and you should try this with your calculator, it comes out to approximately 3.17. Now, that's the natural logs. Now, how about if we use common logs? So instead of a natural log, we'd use common logs. That comes out to 3.17. And in a sense, we have, as long as our bases are the same here, taking the log of both of this gives us the answer of 3.17. So this leads to what is called the change of base formula. And this should be a big star in your notes here. Change of base formula. That if we have log base b of x, that is equal to log of, and that could be natural log or common log, divided by the log of our base. This is the shortened form. And again, we'll have some practice to check it out. So for example 5, here are 3 examples, and we'll use the book. They do a nice job and kind of keep it condensed. So A, this is our original. We're going to use the change of base formula, and here I see they're using natural log. So natural log of 15 equals the natural log of 7. And put that in your calculator, you get this. Now here, for example B, they're using common logs. Common log of 3, and then common log of, I would put here 0.5, but you could put in parentheses 1 divided by 2, close parenthesis, comes out the same. The answer is a negative 1 point. Remember, negative exponents simply mean that they're going to be fractions. And then here, log of base pi, again, 5 would be our common log here of 5 divided by common log of pi, and you get this. I know this tape is going to run a little bit long, so we'll try to keep it as short as we can, but still give you the background to this very challenging material. Now for some more background material, applications of logarithmic functions. Pause for a moment and read this. And perhaps you could pick out that the inventing of logarithms is given to John Napier back in the end of the 16th and early 17th centuries. And what you're also picking out here is that when we have numbers in scientific notation, that sort of goes hand in hand with the use of logarithms, because exponents are often used to indicate really big numbers here. Now, as we continue to go down here, we get to what is called the pH scale, for those of you who've had chemistry. we speak of the hydronium ion, which is H sub 3 O, so there's 3 hydrogens, 1 oxygen, and the overall charge of this is positive. And we define this pH scale going from battery acid that's super acidic to various things in life. I like this. I used to teach general science back in my high school days as a high school science and biology teacher. And we get to see pH 7 is pure water, where there's, we say neutral in terms of acidity, alkalinity, and then liquid drain cleaner. This is a strong alkaline here that's very dangerous actually, as with battery acid as well. So to give you an idea of background, and we're going to use logs to figure these things out. Now for example 6, we'll call upon the authors to give us their presentation of this example via video.
The following example is an application of logarithms. Our example says, if a sample of orange juice is determined to have an H3O positive concentration of 1.58 times 10 to the negative 4 moles per liter, what is its pH? Well, by definition, pH is equal to negative the logarithm of 1.58 times 10 to the negative 4. That is negative. And now evaluating the logarithm of 1.58 times 10 to the negative 4, I get negative 3.80. And simplifying the two negatives, I get a pH value of positive 3.8.
Now, when I did the practice, they didn't give me this formula. So be sure to have this in your notes somewhere. The pH of something is the negative log of its hydronium ion concentration, which is basically substituting this value here for your ions. Now, when I put negative log this into my calculator, I got this. Here they're saying if you had a positive log, since this was negative, the opposite of that would have been a positive number. But putting this into the calculator, I got this. All right, so you'll have to try these. Be sure you know how your calculator works and what the formulas are. Now, another background item is earthquakes. So take a moment to read this over. I'll scroll up slowly here. So you've heard this. They say something on the Richter scale. This is its intensity. And again, this is the formula that you will need to put into your notes so that you can do it. Now there's a whole range of what the earthquake is like, to minor, to light, to moderate, to strong, to major, and great. And keeping in mind that this is base 10 common logs, so every increase by 1 is actually a magnitude of 10. So as we get to higher numbers, that's really something here. Now, keep in mind that I sub O is the rank of what it would be compared to as a ratio. So if something has a low rating of, let's say, 1, that's actually 0 because log of 1 is 0. Anything to the 0 power is 1. Going on to example 7 now, the Richter scale. Here in India was this many times as intense as a 0 level earthquake. And of course, these are recording devices. So let's follow through with what is shown here. Take a moment. We'll use this to put in our notes, and I'll go over it shortly. Let's tease it apart a little bit. Here, this is in standard notation. So to put this number in scientific notation, a little review. It's going to be some number between 1 and 10 here. And this will be to the power of 10 to how many places? Well, we start here. This is where the dot is. And we go over 1, 2, 3, 4, 5, 6. So we're going to move that over 6 places to get this, and this then becomes 7.94 times 10 to the 6. All right, and this is 1. So we have log of this times this, which we convert to its expanded form. Now, this part here is a little tricky. Let me do it for you. It's log base 10 of 10 to the 6. Take our 6, put it out in front, and we get 6 log base 10 of 10, which is just 1, and that's where they get the 6 from. Put this in your calculator, get a value, add 6 to it, and rounding it off to 1 decimal place, you get the Richter scale value of 6.9, which is a strong earthquake. Continuing with background information, we're looking at the decibel scale. Again, this deals with sound intensity, is measured in decibels, lowercase d, and then a capital B. And notice we're using logs. So again, write this in your notes. The decibel rating is 10 log of the ratio I over I sub O. And take a moment to read this. So you see 60 would be great, 80 heavy traffic, but 120 loud rock concert. But if it gets to 160, you start damaging or will damage your eardrums. When I was with the Air Force as a teacher at their schools in Europe on Air Force bases, all of the flight line personnel had earphones that were sound suppressors. And of course, many, may not have been as careful as they should be and have lost sound, resulting in age deterioration to their little microfilaments in their internal ear areas. They can't hear too well. Here they're showing us a device, and actually there is a free device that you can have on your cell phones where you can download the app and check out the decibel levels here. Okay, let's go on to an example now. This is example 8. So we're given the values for I sub O, and we're giving this watt value of 50. So let's put it in our decibel formula. It's 10 log of 50 divided by this. Notice that a negative exponent just comes up, and we're changing this. Let me write this out for you. We're changing the 50 to scientific notation, and we're just moving the decimal place over one place. So this is 10 to the first. They're leaving that step out. So when we bring up the negative 12 from the bottom, it's a plus 12 using our rule of exponents. So that's where we get the 13 from. And you can just put this in, 10 log, parenthesis, 5 times 10 caret 13, and you get the decibel reading of 137. Now you should try this on your calculators and then be sure to write the formula down so you'll know that when you do the practice. I just did it on mine and I got 136.98, round to the nearest whole decibel, 137. All right, we're almost finished. And here they're showing us how it's put into the calculator. Now in these last two slides, they're just going over logarithmic regression. And again, the use of the TI-84s and other calculators do help model this, and it goes through this. We're not going to do this in any great detail. I didn't find an example in our practice, but here's one just giving you some data that you put into your calculator, and if it's used in your class, you sort of get an idea of what the regression curve would look like. And it says next to continue into the practice mode. So this winds us up.